real quick, what comes to mind when you think of an atom? All right, just type in a word. So small was the most common thing that we got. All right. Building block, electron, ball. I like it. Smallest unit, proton, infinite. Okay. So from that, can anybody tell me basically what is an atom? And we've probably heard it defined as the smallest building block of matter, right? Or something like that before. How do we tell the difference? If I got an atom of hydrogen or an atom of helium or an atom of carbon, what's the difference?
Protons, neutrons.
The protons, neutrons, and electrons. Yeah. So we actually define an atom by, first of all, let's define that. Atoms are made of subatomic particles, protons, neutrons, and electrons. We define an atom by the number of protons that are in it, okay? Hydrogen atoms all have one proton. Helium atoms all have two, okay? If you look at a periodic table, the atomic number, the big number that's on there, is the number of protons that that particular atom has. Let's give you a little context here. So they are the building blocks of matter, just like we said. The smallest identifiable unit of an element. Remember, an element is one of those pure substances we can't break it down. 91 or 92, depending on who you ask, naturally occurring elements or atoms. We've made up to element 118 in the lab. So we've made roughly 25-ish different synthetic elements in the lab by slamming things together near the speed of light. So way forever ago, in about 400 BC, these guys, Democritus actually, is the first person to come up with the idea of an atom. He said if you take some piece of matter and you cut it into smaller and smaller and smaller pieces, eventually you're going to end up with a tiny indestructible particle. And he called it atomos, which means indivisible, right? Unbreakable. So this is kind of the first idea, at least recorded idea, of where an atom might come from. Now, is that what he meant when he was talking about it? Who knows, right? But this is the first place we got it recorded, okay? So now fast forward to 2,000 years later, and Dalton gave us an atomic theory, right? And that theory has three parts. He says every element is composed of tiny indestructible particles called atoms. Well, he straight stole that from the guy 2,000 years before. And then he says all atoms of a given element got the same mass and other properties that distinguish them from atoms of other elements. And that's true. And it's kind of framed in a weird way, right? To think about it in terms of mass like that, because we know now that it's number of protons that really define the atom. But you have to think about when this was done. This was done in the 1800s. They didn't have fancy instruments like we have today, and they couldn't go in and look at, with an AFM, what an electron cloud looks like or something like that. So everything they did had to be done on the big scale, on the macro scale, with weights and measures. The third component of his theory says that atoms combine in whole number ratios to form compounds. And we know that that's true inherently, right? We know H2O, CO2, all those things that we've talked about, those are molecules, and they are combinations of atoms. But these were the three basic ideas of what atoms were and loosely how they worked. 100 years later, a guy named J.J. Thomson came up with the electron. He discovered the smaller, more fundamental particle inside an atom called an electron. And he said, hey, these things are present in all atoms. It doesn't matter what kind of atom I got, these things are there. And they're negatively charged. So he came up with a model of what an atom should look like. And this is what he said an atom should look like. And we know that this model is wrong, okay? But this was his model. He said, you've got these electrons, which are negatively charged, and then you got this overall big blob of positive charge, because the charge of an atom has to be neutral, right? There has to be zero charge. Otherwise, when you touch it, it would, decompose whatever you touched it with. It would have an electrostatic interaction. It'd be a bad day, right? So matter's electrically neutral. And he said, well, it looks like a plum pudding. So the pie filling, if you will, is positively charged, and then you've got these little pieces of negative charge in there like pieces of fruit in a pie. So we wanted to test that out and see if it was correct or not. So in the 1900s, Rutherford came up with an idea to test this theory. He said, let's take some alpha particles, which we know now are positively charged particles, and let's shoot them at this gold foil, so a real thin piece of gold. And if the plum pudding model is right, the particles should go straight through, because those positive things should interact with the negatively charged electrons very minimally. It should pass through the positively charged plum pudding stuff, and it should go straight on through. And what we saw is most of it did, but some of it bounced off of something, it looks like, because they got deflected in some way, right? So we've got a detector over here, and we saw, hey, some of the particles landed here, some landed here, some bounced almost completely off. And from this, they said, that plum pudding model is probably wrong. And this helped us define the new model of the atom, which is this. The nuclear model of an atom says an atom is mostly empty space. In the center of that atom, you've got a really dense portion of protons and neutrons, so positively charged and neutrally charged subatomic particles. And then the electrons are in this cloud area outside of the nucleus, right? And so the simplest model to think about is think about it kind of like a solar system, where the nucleus of the atom is the sun, and the electrons are moving around that like planets orbit the sun.